Hi, good morning, and welcome to this live streaming webinar titled Designing Electrodes, or designing rather screen printed electrodes for functionality and commercialization. I'm just going to jump straight into it because a lot of you have had a personal sort of invite from me, so I do appreciate you coming along this morning, and we won't spend lots of time sort of introducing the company and introducing myself. So let's just jump straight into it. So the agenda this morning, we are going to cover quite a lot of topics. So if I go fast, it's because there's a lot to say. We are talking about designing screen printed electrodes, both for functionality, you want them to work effectively, and you also want, at least if you're ever any kind of conversation with Zimmer and Peacock was really about commercialization. So the agenda is, let's talk about substrates. When I mean substrates, I'll just hold this up to the camera quickly. The material upon which you're going to print, we will cover that this morning. And we will talk about inks, gold, platinum, carbon, for example. We will talk about those. We will talk about insulators. We'll also talk about reference electrodes. We'll also talk about size. So this morning is all about commercialization, how to design an electrode, and then sort of when designing an electrode, you have to kind of think about its commercialization. And something that's really overlooked, I want to say a lot, is actually size of that particular electrode. We'll talk about singulation. So I'm sure you're not all super new to screen printed electrodes, but if you are sort of new to them, screen printed electrodes are actually manufactured either in reels or in sheets, or really a hybrid of the two, where sheets it's done in a reel and then cut into sheets. But the way they're sold, they're often, now not from ZP necessarily, they're often sold in what we call singulated form, and that's actually a bit of a problem because it makes people think that this is a screen printed electrode, and that's the end user's experience of a screen printed electrode. But when you're commercializing, and you'll really think when you're commercializing, you're really thinking about manufacturing as well. You've got to understand that the format that they're producing is a sheet format, and you really want to remain in that sheet format as long as possible. And by the way, there's no need to take detailed notes because we will be, I'm recording this, and by attending, you'll get a recording anyway. So we'll talk about singulation. We'll also talk about expanding sort of, the one working electrode to two working electrodes as well. We'll also talk about feature size. I mean, I can just say it now. It's good not to go below electrode sizes that are sort of greater than 200 to 300 micrometers. You can, but it's all about yield after that. We'll also talk about reproducibility. I think one of the biggest problems in commercialization is actually reproducible screen printed electrodes. And then we'll just do a quick summary at the end there as well. So with 2 minutes in, let's go a little bit, let's say faster. So, I mean, if you look at a screen printed electrode, this is ZP's 501 carbon screen printed electrodes. When you're designing such a, let's say, such a screen printed electrode, you kind of got, first of all, you've got your substrate. So when you're sort of designing these things, you've kind of got to think, right, I've got this canvas, and the first layer that you're going to potentially develop or design is the print that's going to define your working electrode and counter electrode. I've kind of made them the same materials here. Sometimes I get inquiries, or ZP gets inquiries that says, I want a gold working electrode and a platinum counter electrode and a silver chloride reference electrode. And it's sort of kind of crazy, really, because they're asking for three materials there. And all they're doing is translating something that they've done in the lab. And they just say, right, well, this is what I've done in the lab. I had a gauze counter electrode. I had for example, a gold disc electrode, and I had a silver chloride reference electrode. So they're literally translating that experiment into an SPE, a screen printed electrode. But in asking, can I have, a platinum counter electrode, a gold working electrode, and a silver chloride reference electrode, they're basically asking for lots of processes and quite lots of expensive materials, and that's it's not a very good idea when it comes to commercialization. So anyway, you're designing your screen printed electrodes. I'll use my 501 as an example. So the first kind of layer that you're trying to develop is this, trying to design is this kind of print here, which is defines the working electrode in this case and the carbon electrode. After that, you may have a layer which is your reference electrode, and it's also your conductive tracks. Sometimes gold and platinum, when you're using those kind of inks and materials, they're quite conductive. Sometimes some carbon inks can be less conductive. So sometimes you can see that actually we're augmenting the tracks for our carbon electrodes, in this case, with an overlay of silver print. And then you kind of come in with the insulator, because the insulator will cover up the tracks so that because otherwise the tracks will be part of the overall area of electrodes. So we cover them up, but we do leave exposed the working counter and reference. Now, if I dig in a little bit deeper on this, I'm just going to move some things here. If I dig in a little bit deeper here, I'm just going to go back slightly. Just to kind of say that, when you look at a screen printed electrode, there's a sort of two main domains on this. There's the kind of proximal end and the distal end. I'm sure you know this, especially if you're using screen printed electrodes already, but when you're designing this, try and follow, there is definitely a convention, when you look at the commercially available screen printed electrodes, there are lots where we have the kind of working electrode in the middle, the counter electrodes in this perspective on the left hand side, and the reference electrode in this perspective looking from the top on the right hand side, and the corresponding contacts are down here. It's good to follow this convention, because then it means you're kind of easier to work with. I mean, there's a potentiostat here, so I've got a potentiostat here. When you work with those kind of conventions, then it's easy to work with off-the-shelf potentiostats. And some of you will have already potentiostats in the lab, and if you follow this convention, then it's easy to use the kind of connectors, etc., that come with that. So even though you want to be creative and design your own electrodes potentially, don't be so creative that if you can follow some of these conventions. Now, I sort of jokingly put a star up against the 501, because what I'm kind of saying here is this is a really good design of an electrode. And why do I say it's a good design of electrode? The first thing I'm going to sort of say is that it's a good size. Now, I'll come back to this point in a minute, but the ZP501 carbon electrode, for example, or many of our gold and platinum electrodes, they're good size. And what I mean by a good size is they're not too small and they're not too big. It's a little bit like there's a story in Europe, Goldilocks and the Three Bears, where they eat porridge and it's not too hot and it's not too cold, sort of thing. This is a good size. It's not, as I say, it's not too big, it's not too small. It's not too big, so it's efficient to manufacture. It's not too small that it's not handleable. I'll come back to this point in a minute, because people send in designs where essentially they're very big. Yeah, they are big. We've got well-proportioned electrode area. So I was told by one of our competitors once that they really liked our electrodes. And I was kind of, why is that? And they said, well, what it is we don't get the counter electrode the right size. If you don't get the counter electrode either the right size or made from the right material, then what happens is you have a large compliance voltage. So, a lot of people now are trying to make point of care, point of need technologies. They're making wearable sensors. All of these applications are low power. When you don't have the counter electrode sized appropriately, and one of the major manufacturers of a USB powered potentiostat told me that, in fact, some of their electrodes don't work very well because they have a problem with the compliance voltage. The compliance voltage is the voltage you apply to the counter electrode in order to allow the working electrode to work properly. With ZP, we have a good ratio between our working electrode area and our counter electrode area, which means that we actually have quite a low compliance voltage. So when I put the gold star against the ZP501, it has some good design principles. Good design, both from handleability and from manufacturability. Good proportion between the working electrode and counter electrode. We use a standardized connector, so you're going to hear me talk about this connector a lot. This connector has a long history in this market, and though we didn't invent it, we definitely are using it, and I would encourage you to also kind of use it as well. The other thing that makes this a really good electrode is actually the quality of reproducibility, and the quality / reproducibility doesn't come, well, it does in part come from design, but it actually comes in part from the fact that we're an ISO 13485 business, so we have a very good quality system. And many of those things, at least the good size and the reproducibility, means actually we give a very good price. I'm just going to kind of slightly change direction a little bit, and sort of, when you think about screen printed electrodes, I mean, I'll hold a sheet of them up here. We're often thinking about these kind of rectangular designs. Now, the kind of length and dimensions on these, I put the title here, Wearables. You know, the world is changing, and in fact, if you're trying to make a wearable biosensor, especially if it's an ion selective electrode. So at ZP, we do sodium sensors, potassium sensors, chloride sensors, phosphate sensors, calcium sensors, all sorts of ion selective electrodes. If you're trying to make a wearable sodium, potassium, ammonium sweat sensor, for example, you don't necessarily need that entire dimension. So you don't need this length, so you can shorten it. These are going to help you scaling these electrodes to be appropriate for wearable applications. And also you don't need, when making ion selective electrodes, which are potentiometric measurements, you don't need the counter electrode. So suddenly you can kind of scale down these electrodes quite a lot. So if you're designing, if you are designing wearable biosensors, then you can actually get rid of one of the electrodes in your design, and you can also shrink it fairly well. So we've got the working electrode here, we've got the reference electrodes and the connection points for that working and reference as well. I'm going to talk about substrate in a minute. So the definition of substrate is, here's a couple of screen-printed electrode sheets from ZP. The materials that we're printing upon, you know, that's what the substrate is. So you've got some choices on substrate. PET, polyethylene tetraphthalate. This is really a it's the material most used. It's the material, if you, this is a commercial glucose strip, for example. This commercial glucose strip that I'm holding up in my camera here, this is made on PET. So it's very well used. It is used a lot in the medical sort of space. Polyimide, especially now that people are very interested in wearable sensors, people are interested in making sensors on polyimide. So when you're designing your electrodes, PET, polyethylene tetraphthalate, is a good material to think about. Polyimide. I wasn't so aware of this, PVC, polyvinyl chloride, and I think this PVC material is used a lot in academia, probably because it's cheap. Unfortunately, I got a suspicion that PVC probably has a lot of plasticizers in it, so it'll have an okay shelf life, maybe for about 2 years, but maybe it gets brittle over time. Maybe it's a bit too soft and it reacts with the ink. So we don't use PVC in it, but I was aware that it's getting used. We do use ceramic on occasions. Ceramic, when you look at the sensors on the R&D market, they either tend to be made on ceramic or they tend to be made on PET, or you've got people like ZP that make both on ceramic and PET, polyethylene tetraphthalate. Ceramic is a great material for making, if you want to make a very pure gold electrode, for example, a very pure platinum, ceramic is a good material for it. But it doesn't scale well when it comes to commercialization because it's actually quite expensive. But ceramic is used. Now, paper, I think it's really sort of, first of all, paper is used in biosensing. I mean, lateral flow, lateral flow strips are either used for SARS-CoV-2 detection, or they're used for pregnancy tests. So lateral flow is mostly using cellulosic material. So paper has a role, let's say, in making biosensors, but it's not necessarily a good substrate when it comes to actually making electrochemical sensors. I remember something like 2018, 2017, I was getting contacted by a PhD at the University of Florida, and she was sending me data of her carbon printed her carbon printed on paper electrochemical sensors, and they were just really distorted. And I've sort of realized there that actually when you print on paper, it does lead to the ink soaking into the paper. There's a lot of separation, and it doesn't lead to a very good quality electrode. You don't necessarily need a good quality electrode to make it a commercially available biosensor, or commercially viable biosensor, I should say. But it was, in the end, I think it actually led to reproducibility problems. So paper was fashionable. I mean, there's a George Whiteside has been sort of making these kind of paper-based microfluidics, and I think that's inspired people to try and explore paper, but there's no commercial example of paper. So your sort of low-risk routes when it comes to designing for commercialization, PET is low risk, polyimide is low risk. Ceramic is an option, but ceramic is harder to scale. So we do make them out of ceramic. They do lead to very high quality electrodes, but it is an expensive material to work with. Now, when it comes to designing electrodes, you kind of, sometimes the ink that you're going to use on this working electrode, you don't always sometimes that's governed by the actual assay that you're trying to develop and the analytes that you're trying to detect. But you've got this choice of gold, platinum. I sort of put carbon graphite here. These are the kind of three most commonly used materials. You do have some availability for mediated carbon. There's a time and a place for mediated carbon, and it really depends on the application. But by default, if I had a choice between using carbon or mediated carbon, I think I would actually just be using carbon. Graphene is not, I don't think it's a particularly good idea to blend graphene into an ink and print it. You basically end up losing the properties of graphene that you're otherwise hoping to get. Carbon nanotubes, most of the time when people are using carbon nanotubes, they're not putting them into the ink, they're depositing them down. Mexines seem to be something that's quite popular at the moment. The only thing I would say about these, I'm not going to call them exotic, but you've got graphene, carbon nanotubes, mexines. I mean, I'm even going to put the word etc. here, or sorry, nanoparticles. We are actually running a PhD at the moment where they're using nanoparticles. I'm not going to sit here and tell you that nanoparticles are the greatest thing when it comes to making inks and biosensors. They're useful enough. Their usefulness is that you can, rather than necessarily using platinum or gold, you can use nanoparticles and sort of argue that you're saving some money that way. But there's always new materials coming. So if you are serious about commercialization, you don't really always need to use the most exotic material. And I know graphene doesn't sound that exotic, but it's fairly hard to scale when it comes to biosensing. So you really, and if you had the choice between graphene and graphite, I would definitely take graphite every time, because we're talking about commercialization, how to scale quickly, not how to spend years perfecting materials that don't exist at the moment or processes that don't exist. I mean, it's probably worth just highlighting on gold at the moment. I mean, if you had the choice between carbon and gold, I would definitely take carbon. Gold at the moment, if you want to buy 25 grams of gold ink, it will cost you about 3,500 euros. That will produce you about 6,800 SPEs. 3,500 euros for 6,800 SPEs is over 50 cents or euro cent per electrode. So when you kind of say, oh, I want to make, I want to develop something that's low cost, easy to use, and that's often what people say when they're thinking about SPs, screen-printed electrodes. Gold is not your friend when it comes to that. It's already giving you 50 cents worth of cost just in the amount of gold that you're using in the first place. Platinum has also got some cost, some problems when it comes to cost. Carbon definitely doesn't have those costs. I wouldn't necessarily default to mediated carbon inks. It's very hard to actually get enough mediator into those inks to always be useful. Graphene, you don't print ink. If you want to make a graphene electrode, it's a sort of secondary process that you do on top of your carbon printed inks. At the same time, you don't put carbon nanotubes into inks. You may drop cast them as a secondary process. Mexines are the same, and nanoparticles. Yeah, you definitely don't put these into the ink because you don't want them in the bulk of the ink. You want them on the surface of the ink. So you would do it by drop casting. And as I say, I put etc. here. So mediated carbons, you can electropolymerize these onto the surface, or you can put them into the ink, but it don't always get a high loading because it's very hard to dissolve those mediators into that ink. Carbon nanotubes, you drop coat. Mexines, you would drop coat. Nanoparticles, I would say you would drop coat. When it comes to ink formulation, I mean, if you're so interested, it's actually not that hard. The recipe is quite simple. I suppose it's the processes that are hard, but one can make a carbon ink, for example, by mass. We're putting in something like less than 10 micrometers of carbon flakes. You're adding even smaller particles of carbon so that it all packs nicely together in a kind of ratio of about 4:1. It's all bound together using an organic binder. The solvent is only so that it essentially is sort of semi-liquid, a viscous fluid, so that you can actually print it. And then you may add some additives to stop it sort of foaming, etc. So what happens in reality is when you print this, you actually remove most of the, well, you definitely remove the solvents because that's called curing. And so really you're just left with this kind of carbon and it's bound together by the filler. So you've got approximately 60% carbon in that final print. You can then, if you so wish, start adding mediators like Prussian blue, but it is quite hard to actually dissolve Prussian blue in these inks. So the recipes are easy. It's probably the processes that make it hard enough. I don't think I would actually suggest that if you were commercializing that you necessarily make an ink unless it's somehow linked to a kind of PhD that you've done or something like that and you have a lot of experience in it. Otherwise, you're getting into this kind of whole drama of making an ink before you even start making the screen printed electrode. I've shown this slide before, so I won't spend on it too long, but I have done calculations on the current price of platinum per gram, the current price of gold per gram, and the current price of carbon per gram. So when I kind of suggest that actually you don't go for gold, for example, by default, you may use carbon, it's because gold is 179,000 times more expensive than carbon. So carbon, when it comes to making low-cost SPEs, if you were starting out in a research program and you said, right, I have to make some key decisions now, my key decision would be, and the key decision, you were actually genuinely thinking about commercialization, I would definitely start with carbon, or yeah, I would definitely try to avoid gold and platinum. Sometimes you can't because there's for example, there's a lot of science in the aptamer space at the moment, in the immunoassay space where people are using self-assembled monolayers to make biosensors, and I could really see why actually gold was their preference there. What I'm showing here is the reference ink. So most of the time at ZP, we're using silver chloride. I asked the question here is actually, do you need to print silver chloride? When you're doing R&D, I mean, Zimmer Peacock, if I hold up one of our electrodes, we definitely have silver chloride reference electrodes up on our electrodes. There's no doubt that we are printing silver chloride. I will show you in a minute that actually when you look at commercial sensors like this glucose strip, in fact, there is no silver chloride in this glucose strip. So people sort of think that they always need silver chloride. You have to be quite smart not to use silver chloride. At ZP, we can actually advise people how they can avoid it, but by default, our electrodes do have silver chloride. Why do you want to avoid it? Because of cost. But you don't actually necessarily need silver chloride to reference electrodes. So if you could manufacture a complete SPE, screen printed electrode, just by printing carbon. And I kind of call that one print. Now that's really easy to manufacture. But I sort of say that its performance may be a little bit less than perfect. It may be good enough. And by the way, when I say it may be good enough, there are, as I say, lots of glucose strips in the market where they definitely are using this kind of idea of just one print of carbon. In fact, I think it's the Johnson & Johnson One Touch uses this. So avoiding silver chloride and avoiding precious metals altogether and just using carbon to actually do all your electrodes is an option. It's easy to manufacture, but the performance can be a little bit it's harder to would be harder to publish because the data would be somewhat distorted. But from a commercialization perspective, it can work. Now, most of the SPEs that, and I would sort of suggest that this is a good place to start, was actually you do actually print your carbon and so your working and counter, and you print your reference and your conductive tracks out of silver chloride. This requires 2 layers and 2 prints, so that's a good place to start. So it's okay to manufacture and the performance is good. I've seen this happen, and don't do this, where actually what people are doing is they're printing their counter electrode, their working electrode, then they're putting down some conductive tracks, maybe out of silver, and then they're printing their silver chloride. You don't need to do that. You could have used the middle option where actually the silver chloride is used both for the conductive tracks and for the reference electrode. It's overkill to kind of print down silver and then print down silver chloride as your reference electrode. That's 3 prints, so it's not good to manufacture, but the performance will be excellent. It's just every time you do a process, it's going to add cost. It's going to affect your yields. The less processes you can do, the easier it is to manufacture. So the middle ground is, which I've indicated here, which is 2 prints, is probably the best, let's say, trade-off. Just on a commercial example, when you look at this when you look at this SMBG, this self-monitoring blood glucose strip, if you pull them apart, I've looked at this, there's no silver chloride in this. They're actually using ferricyanide as a reference, as a pseudo-reference electrode in this particular case. If you're not sure on the term pseudo-reference, ZP has done videos about that in the past. Just coming to the insulating layer. So the insulating layer is that kind of layer that stops liquid necessarily touching the conductive tracks, and it helps to define the exposed electrodes. So and it's such an insulator. Again, I'm not suggesting you really go out there and develop insulators. You know, I would actually come to a contract manufacturer like Zimmer Peacock and just let them use their standard materials. If you are so interested, these insulating layers are often using aluminium oxide and bisphenol A to bind it all together. So that's an epoxy resin. Sometimes if I'm sort of mentioning formulations here, I'm mentioning it more for kind of interest, but I'm not necessarily suggesting that you go out and start formulating insulators. You can sometimes ask yourself the question, if I formulate an insulator, what problem am I solving? And you're not solving any particular problem. I mean, they already exist, and there's probably a few hundreds different insulators out there. The question I ask here is, do you actually need to do an insulator? And I'll again use the glucose strip to actually show you that even though at ZP, you know, we do something, we call it the food sense, where we have these kind of we have these electrodes. We do use insulators in our commercial products, for example. But if you look at a SMBG, a self-monitoring blood glucose strip for measuring glucose in blood for diabetics, if you pull it apart again, there is no insulator in this. What they're using is they're actually using this tape, which the tape is also helping them design their microfluidic, but it's also working as their insulator and covering up the tracks. So what they've done is they've kind of got this electrode array or working counter reference, for example, and they're just using tape, sticky tape, actually, as their insulator there. Screen printed electrode size. So I am going to talk about screen printed electrode size now. I'm actually just taking a sip of water. But I'm going to use SMBG, self-monitoring blood glucose strips. I think what people don't do enough of is actually look at commercial examples of biosensors and printed electrodes, because if they did, they would sort of get some good tips. When I look at this this glucose strip, which I think is from Essentia, this one, which is probably from Roche, and this one, which is from GlucoRx. Now, the Roche one is the one that's been on the market the longest, and it's actually quite big. So I do put it in there because it's quite a big electrode. But the other two, if you'll notice, are actually quite small. And so when I say to you, it's a good idea commercially to make your electrodes a little smaller. And when I say a little smaller, you know, I'll sort of tell you in a bit about the dimensions, which is about 7 millimeters by about 23 millimeters. But watch for that slide. When I say make it a little bit smaller, I'm not just saying this. You can also learn this by looking at commercially available products. What's happening is there's lots of vendors on the market serving the R&D market who are selling screen printed electrodes. That's great, lots of competition. But the problem is that these electrodes are actually quite large on occasion. So if you think, oh, I'm getting a great benefit, I've got this large electrode. But this large electrode is sort of, step one is putting you in a path rather that's harder to commercialize later on. So you really want to start off on an electrode gross size that is commercializable, and I'll show you why I say that these are harder to commercialize upon. So they have quite a large area. These are to scale. So this is what a ZP electrode looks like, 7.2 millimeters by about 26.3 millimeters. So when you're designing an electrode and you're wondering what kind of dimensions grossly to have, you can see that these are off. The larger one is not ours and the smaller one is ours. These are not bad dimensions. Now, if I divide the third-party SPE area by the ZP area, it's about 1.82. And if I round that up to 2, so that says that approximately area-wise, ZP is half the area of many of the otherwise larger commercially available SPEs. The problem with that is that actually, especially when you think about commercializing later on, the cost is actually proportional to the materials. And the materials you use is proportional to your area. So to scale up that, when I say scale up, to commercialize on that larger area, it'll actually cost you twice as much as if you were to scale up on a ZP SPE. So people go into the lab, they find some SPEs around, they start using them. They're actually quite large, and that largeness later on will make it harder for you to commercialize later on. The other problem with largeness is not just the materials you're using, it's also your rate of manufacturing. So your cost is inversely proportional to your rate of production. So when you have a sheet of large electrodes, you can fit about 164 SPE screen printed electrodes onto that sheet. Whereas if you use the ZPE size, you actually get 300 electrodes onto that sheet. So you can see that we're approximately got twice the packing density of SPEs on otherwise the same sheet, which means our rate of production is actually twice that of the larger electrode. So that means that in the end, that the cost of that, the long-term cost of using the larger SPE will end up giving you a cost that was otherwise 4 times what it would have been if you'd actually used lessons or that way that I'm giving here. So don't make your electrode too big. 7.2 millimeters by 26.3 millimeters is a good size. So there's a problem, see, because actually people are, especially in research, you know, there's this inertia that people always do what the student before them did or what their supervisor has said. So they are using these large electrodes, and these large electrodes have essentially large working electrodes on them. So once you start on the course of either developing an assay, which may be impedance, it may be amperometry, it may be square wave voltammetry or differential pulse voltammetry. Once you start on that, all your data, all your algorithms are going to be developed to work with that size of electrode. Now, when somebody like me comes along and says, well, in fact, it's hard to make that into you can make your life easier by using a slightly smaller electrode and therefore getting a cost benefit when you scale up. It's very hard for you to then sort of go back and say, okay, well, now I'm going to use that suggestion from Zimmer and Peacock, that I'm going to use these smaller electrodes where maybe my working electrode has a diameter of 2 millimeters. Fundamentally, your assay will still work. When you go from 4 millimeters to 2 millimeters diameter, you're not changing the physics regime. You know, that's not a change that's not an order of magnitude change. You know, there's a change, but, you know, the signal will change. And I've sort of represented it with this idea here. But you can still get signal out of this. Now, the problem that you're going to have is that, you know, if you've done all that work and there's all this predicative work, you're not going to want to then say, okay, well, that's fine. That was great. I move into a smaller electrode. So what I'm saying is start on the right foot, actually start on an electrode that at least is sized that you could commercialize it. So be aware of using too large an electrode with too large a working electrode in your R&D phase. And of course, I'm biased because, you know, well, I'm not biased. I'm biased because we do commercialize assays on screen printed electrodes. And I realized that, in fact, you know, we can produce hundreds of sensors on one sheet because of our size. And I think you should also benefit from that as well. Something that this is a bit of a thing with me, that I realize that people are buying SPEs. Now, some manufacturers will give you SPEs in sheet format. I'll talk about ZP does that as well. We do it what's called singulated and sheet format. I want to kind of say you should be buying your SPEs in sheet format, and I'll sort of explain that now. So a ZP, you know, if you're designing your electrode, don't think that your electrode is a singular piece. It's actually going to come to you probably in some sort of sheet form or some sort of roll-to-roll form. That's important because it will help you in manufacturing. First of all, to know it will help you in manufacturing. But we do sell in sheet format. So for example, you can buy sort of 300 sensors on a perforated sheet. You can also buy them singularly as well. But I actually think you lose a lot of information when you singulate, and I'm going to explain that now. So if we take the sheet, what we're actually doing is we're perforating the sheet so that you can just easily remove an electrode. That's important, see, because when you're commercializing, you need as much order in your manufacturing system as possible. So when you singulate, you're going from a very ordered state to a very disordered state. So we've overcome this problem by actually selling in the sheet format. So it's all ordered for you. You know, you've got a sensor in position A1, a sensor in position A2, a sensor in position B2. You know, the sensors are all in a grid, but it's perforated, so it's quite easy to remove. So when you're designing electrodes, you can also design it this way as well, that actually you can sort of order in this perforation technique that I'm discussing. So it's easy to remove them, but the fact is that when you're functionalizing sensors, when you're functionalizing one sensor, it's easy to drop code on top of it. When you're trying to do hundreds and thousands and tens of thousands and hopefully hundreds of thousands of sensors, you're not going to go there manually drop coating. So in fact, what I've seen is I've seen people really bad ordering in electrodes from vendors and putting them into trays so that they can actually have them in an ordered fashion so that they can then functionalize them, which was crazy because what happened was the vendor, the contract manufacturer, would have produced them in this format. They've then cut them all out, put them in boxes and sent them to them singulated, and then they've tried to reorder them by putting them back into trays. It's kind of crazy. So they went from order to chaos and chaos back to order. So when you're designing, thinking about commercialization, just try and make sure that you stay in your sheet format as long as possible, because then what it means is that if we need to functionalize, we would functionalize for a robot, for example, the robot can just index along. I mean, there's a video running in the background here, but it literally is putting Pico drop down. It's going to be much more accurate, much more quick, much more reproducible than a human being. So staying in an ordered state is a very good idea when it comes to commercialization. And I can't believe it when I see people ordering them singularly and then trying to reorder them in their facility. You can just buy them essentially in a sheet format that's perforated, and then you can use robotics, for example, to help you commercialize. So it's easy to go from an ordered to a disordered state. It's relatively fast to break them up. It's relatively easy to do, but it's difficult to reverse. So that means when you try to go from disordered to ordered, that is difficult. It's slow. You lose information. You don't realize which sensor was in which position at any one time. You've lost loads of information when you do that, and it could have been useful to you when troubleshooting to actually have that information. And if you did think you were reordering it, you're going to make errors. So stay in the ordered state as long as possible when it comes to commercialization. You can actually, I can sort of semi-quantitatively quantify this point a little bit, actually. I mean, the term is entropy. If many of you have a physics or chemistry background, you'll be used to entropy, which is a measurement of disorder or uncertainty. So when we have a monolithic sheet like this with 300 electrodes on it, the number of available states is actually only one. So using the calculation for entropy, the line or the natural logarithmic of 1 is actually 0. So think of it as a chaos, from a chaos perspective or entropy perspective. When it's all neatly ordered, you have one state, and actually you have an entropy of 0. If I gave you 16 electrodes, do you know how many permutations of 16 electrodes there are? Well, it's actually 16 factorial, which is actually over 20 trillion permutations. So in manufacturing, you want to stay as ordered as possible for as long as possible. So I'm emphasizing the point, stay in that sheet format as long as possible. Only 16 electrodes could lead to something like 20 trillion permutations. The entropy of that is about 30 Boltzmann constants. If you took 300 electrodes and disordered them, which is effectively what people are getting these large pack sizes and they're all singulated, this is essentially what's happened. The entropy in that particular case has gone up to, well, first of all, the number of permutations is 300 factorial. 300 factorial is such a large number. There's more permutations with the idea of 300 electrodes than there are atoms in the universe. So you can sort of understand this. It's getting pretty chaotic. So it's a very pedantic way of emphasizing, please use the sheet format and maybe use the perforated sheet format idea that ZP uses in its products. When you are designing electrodes, what your job is to fit as many electrodes in a space that's about 225 millimeters by 345 millimeters. So if I hold this sheet up, you have a print area. Those print areas are on the screen at the moment. Your job when designing electrodes is to get as many electrodes into that print areas as you possibly can. But you can't make them so small. If you make them so small that you can't handle them, it's hard to handle them during the manufacturing process. It's hard for your end user to manufacture them. But when you're designing electrodes, understand that you have this kind of print area, and your job is to use that print area as efficiently as possible. The thing that happens a lot is people say, well, I really like a custom SPE, but I only want one or two sheets. And I want to say the problem with screen printed electrodes is that it's not efficient to print one or two sheets. In fact, the minimum, my sort of manufacturing engineer says 20, but realistically he really means 30. I mean, so you've got to understand that. So for example, if this print area is 225 millimeters by 345 millimeters, we can squeeze 300 SPEs into that print area. If we're doing 330 sheets as a minimum run, that means you're about to get 9,000 screen printed electrodes. So there's very little point in contacting a manufacturer and asking for one or two sheets of a custom electrode, because what are they going to do with the other 28 sheets? So just know what you're sort of setting you up for. I've shown a lot of rectangular designs today. I just want to kind of open your mind a little bit and say, at ZP, obviously, we're just as famous actually for doing really world-leading wearable biosensors. Now, we do this with really well-funded clients. But I just want to kind of point out that some of the designs that we end up doing are also, things like circular electrodes as well. So don't think this is a talk just about rectangular electrodes. And I'm going to go a little bit fast now because I realize that, we are coming up on time. I always try to stick to time. So I'm sort of telling you, look, there's a certain size that you should somewhat stick to. I'm also I mentioned it earlier on, there's a certain dimensions. I'm going to give you the dimensions now of the connectors that I think you should design in. Now this is recorded, so you can actually go back and watch this recording later on. I think you should sort of design 3 layers, 1 layer for the conductive tracks, 1 layer for the working electrode, for example, and then the insulator. Now the connectors that we use, these are pretty standard dimensions, but stick to it. So the length of this SPE I'm asking you to do is 7.2 millimeters. The contact pad for making the electrical connection is 1.5 millimeters wide. The pitch between contact pads is 2.54 millimeters. The height or length there is 4 millimeters, which means you end up with a gap between those electrodes and the edge of about 0.31 millimeters. Design using that kind of connector, it'll mean that you're compatible with us. It makes you compatible with many commercially available screen printed electrodes. Commercially available potentiostats on the market. As I say, I will go quite fast, but just FYI, if you do design along those dimensions, then we will have connectors that can mean that you can slot in your SPE, and you can also make connection using banana plugs to whatever potentiostat you happen to have. People are very interested in putting multiple electrodes onto SPEs. So rather than just having one electrode, they would like 2 or more electrodes. And that you can do. So we have a kind of standard design. But if you want to, for example, add a second working electrode, then go from 7.2 millimeters to something like 9.74 millimeters. Otherwise, keep the length the same. And then all it means on the contact side of things is, your overall length is 9.74 millimeters, the same dimensions on those contact pads. As I say, this is recorded, so you can actually play back the recording later on to find that out. But otherwise, what I did is slip in an extra contact pad for the, in that particular case, so that we could get the extra working electrode in. So we got 1 and 2 working electrodes in the middle there. And that people are quite interested in doing, let's say, multi-analyte sensors. Now at ZP, we've been on a bit of a journey. When we first started off, we used to make mostly rectangular electrodes. And we did it for a good reason, because we were actually very interested in what's called automatic starts, because we were making a lot of glucose strips in those kind of days. But we do understand it's harder to functionalize a rectangular electrode. So we have also gone in the circular electrode direction as well. So it's not a bad idea to generally make electrodes circular, because you can sort of drop cast onto them quite readily. So why round? Because it's easy to deposit, just drop, and things will sort of generally spread out. Talking about feature size, I mean, one of the smallest electrodes we've ever made is a 200 micrometer dimensioned electrode. I don't suggest it. You can see I've zoomed in on this image, and you can see the sort of jaggedness of it. So when you're designing a screen printed electrode, you want it to be high quality and you want it to be reproducible. Stay on the millimeter scale. You can come down to the hundreds of micrometer scale. That's what we've done here. But if you want an easier life, then maybe stay on the millimeter scale is my quick suggestion. Now, I've talked a lot today about printing electrodes and insulating electrodes, and we've talked a lot about design, but I just want to point out to you that when it really comes to commercializing sensors, a commercial sensor may look like this, that we've got this kind of distal end where we've kind of printed the electrode. We may have put some insulator over it. Then we've got the proximal end, which is really the sensing. In this case, we've printed the electrodes. We've put down an enzyme layer, for example. We've laminated. We've created a microfluidic chamber on top of that. So that's really all the processes that go towards making something like a glucose strip. So all we've talked today in this webinar, and I'm conscious of the time, we've been talking for 44 minutes, so I am watching that, don't worry. We've only talked about 2 processes. There's about 18 processes in this one slide alone, so we've only talked about 2 processes. So if you do have further questions, I'd be quite interested to, when I email you all out a copy of this webinar, to hear what you'd like to do in the future. Now, at ZP, I've given you some clues about size of electrodes, connections for electrodes, materials for electrodes, substrates for electrodes. If you are reaching out to companies like ZP for custom work, just do a minimum, make sure they're either ISO 13485 or ISO 9001. It doesn't mean that they necessarily are quality, but just make sure that they at least are one of these ISO standards. And then ask the question, are they fabless? Now, when you look at NVIDIA that makes, the sort of GPU chips, they're really using TMC. Is it TMC? But what I want to say is, in the electronics industry, there's a lot of fabless companies. What I mean by that is that they've got a product, they've got designs, but in fact, they don't really. I do appreciate the feedback, Arthur. They don't really. Many of these people, electronic companies, don't actually manufacture. And what I didn't realize when I first started 12 years ago is it's also the same in the screen printed electrode field, that you are contacting people for custom work. They're actually not manufacturing themselves. So your assumption is that you go to this brand, they may even be ISO 9001. Actually, you think that they're doing this in-house. They've got their own factory and their own people. The reality is check, because in fact, they may be subcontracting, or they actually just may be using academic equipment. And it is basically, in the end, you need to, if you're going to do custom work, you need to be really working with people who control the people and control the facilities. And so if they're subcontracting, the control is less. And if they're using academic equipment, the control is less, because academic equipment, it's harder to maintain, it's harder to ensure that the equipment hasn't become contaminated with other materials. So if you watch many videos from ZP, you'll actually find out that we often make assays that are calibration free. And why is this? Because in fact, we do a lot of, we're ISO 13485, we make a very reproducible screen printed electrode. We do a lot of testing to make sure, so we would test by cyclic voltammetry. We do a lot of testing to make sure that our relative standard deviation in each sheet, let's say looking at peak height versus the average, was single digit reproducibility. Because if you don't have single digit reproducibility, it's very hard then to make a sensor on top of it, because in fact, the sensor that you're manufacturing from it will inherently have this variability due to the electrode itself. Make sure that the company you're working with has some sort of quality system in place. Make sure they actually are manufacturing it, and then you can have also a conversation about how they check for reproducibility. So at ZP, we do a lot of reproducibility. So I've got 1 more minute to go, and I will just essentially summarize with that before I lose my voice. Right, we've talked a lot about materials. PET is a standard material, it's pretty good. Polyimides are particularly fine. Be careful of, and ceramic is also good, it's just harder to scale. Be careful of paper and PVC. If you've got a choice, use carbon ink. You probably will design with an insulator, but just understand that actually pull apart a glucose strip and realize there's no formal insulator there. Size is important. Don't work with R&D electrodes that are too big. Singulation. Order is your friend when it comes to manufacturing. You should singulate at the last minute in the manufacturing stage. Many people are buying R&D sensors that are already singulated. It's essentially a bad idea. Stick to the standard connector that we've kind of otherwise suggested. Design your electrode on the millimeter scale. We've designed and printed on the 100 micrometer scale, or sorry, 200 micrometer scale. It works, but it's reproducible and yield that's a problem. repeatability. Repeatability really comes from, some decades of work, and one of the biggest problems in R&D is actually repeatability of electrodes. So it is probably sometimes good to go to at least talk to somebody like ZP. And that was it. So I will send you all a recording of it. I've gone for 49 minutes. I'm 4 minutes over. So I am going to close up now. But I want to thank you all for your attention. Most of you been personally invited, so you have the email of mine anyway, and I'll send you a recording later today or maybe tomorrow because there's quite a few emails to send out. But otherwise, I would say thank you very much and take care. Thanks a lot. I appreciate the feedback that's coming through. So thank you so much. All right. Take care. Bye bye.